Okay, so we're looking at a displacement versus time graph. Key thing that we're really going to be looking for here is how is the displacement changing over time? And the best measurement of that is going to be the gradient or the slope. And so gradient or slope, we can calculate rise over run, and that gives us a good sense of how the distance is changing with time. Okay, so if we start with question 1, identify the regions of the graph that show positive velocity, zero velocity, or negative velocity. So I'm looking at the slope of these different sections, the gradient of these different sections. I can see that in part A, the displacement is going up over time. So if it's going up over time, that tells me that in part A, this person has a positive velocity. They're moving in the positive direction. During time B, they then go back down. So their displacement is going back towards zero, and that means they have a negative velocity. At time or region C, their displacement doesn't change. That means they're not moving, and they have zero velocity then. In part D, they have a positive velocity again because their displacement goes up or further away from where they started. And then in time E, they're going down with this curve. We'll come back to that later, but they're going back towards zero, and that means they have a negative velocity during time E, during that region. If we actually want to determine the velocity of an object or the person in region A and B, then we actually need to calculate a value for the slope. So for A, I picked 2 points along this line. The easiest 2 points are at the beginning, 0, 0, and at the end, which is 0.5 seconds and 10 meters. So my 2 points are 0, 0, and 5, 10. That means that the rise is 10 minus 0, and the run is 5 minus 0, and so my velocity will be 10 meters over 5 seconds. So the displacement was 10 meters up, and it took 5 seconds to do that. And if I divide those, I get 2 meters per second as the velocity during the region A from the first 5 seconds. If I then look at B, I'm going to do the same thing, rise over run. This time I'm starting at 0.5 and 10, so 5 seconds and 10 meters, and I'm going to end here. Ending there is 8 seconds. At time 8 seconds, the person is now at 2 meters away. So again, if I do rise over run, the rise on the top is I end at 2, started at 10, and I end at 8 seconds, and I started at 5. So I'm going to get a displacement of negative 8 meters. So I went down 8 meters from 10 to 2, and it took me 3 seconds to do that. So in a calculator, you could calculate this. It looks like it's 2 2/3, which is about 2.67 meters per second. And that velocity is negative. It's negative because we're moving in the negative direction back towards zero. And you can see that the slope in part B has a negative gradient to it. Okay, then this next question is the difference between displacement and distance. So it says after 8 seconds, determine the displacement. Well, at 8 seconds, the object or the person is at distance or displacement of 2. So the displacement is only 2 meters. The person is 2 meters away from where they started. How far have they traveled? What was the distance that they traveled? So they went 10 meters in the first 5 seconds, and then they traveled 8 meters backwards to get back to 2. So they traveled 10 meters, and then they traveled another 8 meters, and so in total they've traveled 18 meters. So distance is the total distance that they've traveled. Direction doesn't matter. Distance is a scalar quantity. Displacement is a vector quantity. So it matters that all that matters is how far away are you from the origin. So at the end of 8 seconds, we're at 2 meters position or displacement, and that means we are 2 meters displaced from where we started. All right, if we get to some of these higher level questions, Question 4 says, identify the region with the fastest speed and explain how you know. Speed is the magnitude of velocity. So speed is a scalar value. It doesn't have direction. And the thing I'm going to be looking for is knowing that the gradient or the slope of this graph represents the rate of change of displacement, and so therefore it represents speed or velocity. If I take a quick look, I can see that in the region of D, I seem to have the steepest line. So I would say D is the fastest, and explain how I know. I know that because I have the steepest gradient, and gradient is the rate of change of distance over time. Or I can simply say the gradient is represents velocity on this graph. And so when I see the steepest gradient, that means that's the highest value for velocity. Sorry, that's a little bit messy of an answer. I didn't give very much room here, but that's something that we could say. So we both answered the question. We can see that D is the fastest, and then we've backed up our answer with some reasoning, showing our understanding that gradient represents velocity. So the steepest gradient represents the highest value for velocity. Notice that since this question asked about speed, if this graph had had a really steep negative slope, that could have been our fastest speed. Speed does not care about direction. Speed is a scalar value, so you could have a very large negative slope, and that could be the greatest speed, even though it's negative. Okay, final question, highest level. Describe the person's motion over the course of the 18 seconds shown on the graph. Try to include words like positive, negative, constant or changing, and or speeding up and speeding down in your response to make it as complete as possible. Okay, so I'm just going to go through the regions here. So for A, the person is moving in the positive direction, and I would say they're moving with a constant speed. The reason why I know that is because the way that the distance is changing is a straight line. That means the slope isn't changing. And if the slope isn't changing, then the speed isn't changing. So in this part, we have positive velocity, or the positive direction, you could say, and it's constant. Okay, then during region B, the slope becomes negative, so it's going down. So we're now moving in the negative direction, negative sign. But again, it's a straight line, and so it's a constant speed. Constant speed, constant speed. If you want to get, a little bit more detail, you could say how during B, we're moving faster than we were during A, because it's steeper. But you didn't have to comment on relative speeds here, so I'll leave that out. So during A, we're moving in the positive direction with constant speed. During B, we're moving in the negative direction with constant speed. During C, we're not moving. C is a flat line, there's no slope. That means there's no motion, no speed. During D, positive direction, constant speed. This is our fastest speed, our steepest slope. And then during E, this is really the trickiest part. During E, I can see that we're going in the negative direction, but I'm getting a curve. And when you have a curve, that means the slope is changing. So if I zoom in here, this is maybe a new concept. So let me try to show it more exactly. If you think of it at first, and you try to fit a line along this first part, like that, this line is pretty steep. It's steep and it has a negative slope. If I fit a different line, I'll use a different color, a little bit later along this part, let's see if I can turn that into a line. Is that going to work? No, it didn't quite work. Let's try that again. Okay, so that thing we would call a tangent line. So I'm putting these lines that fit part of the curve. Because it's a curve, the slope is changing. But I can see at first it's steep, and then later, like with the purple, it's less steep. Still negative, less steep. And then if I keep going and I look at it towards the end, then it's even less steep, but still negative. So the whole time during E, we're definitely moving in the negative direction. But because of this curve, the way it's curving, and it's going from steepest to less steep to even less steep, that means the speed is going down. If the slope is going down and getting smaller, the speed is going down and getting smaller. So it comes back to that really core idea on this kind of graph, displacement versus time, slope equals speed. So we're moving in the negative direction and slowing down. And I know that's a tricky new concept, but we can see our reasoning would be that when we look at that curve, we can see that the slope is getting less steep over time. And since slope equals speed or velocity on this graph, that's how I can tell. If it's getting less steep, I have a lower value for my slope, and that's why I know I have a lower value for my speed. That means I'm slowing down. So that's an overview of the type of thing we'd be looking for in these types of data interpretation questions, which is what you can expect when you go to the A3 section of the test.